Hello, myself Amrendra Mani Tripathi from Faculty of Engineering and Technology, University of Lucknow. From Department of Civil Engineering, I give a seminar presentation on flood hazard mapping using software tools. This slide provides an organized outline of the seminar. The key topics include flood hazard, impact of flood hazard, relation between flood hazard and flood routing methods, Flow 2D Pro, case studies, and references. Flood hazard refer to the potential risk posed by water inundation in normally dry areas. These hazards can arise from natural causes such as heavy rainfall, rapid snowmelt, and storm surge, or human-induced factors like dam failure. Mapping flood hazard is essential for assessing risk and devising mitigation strategies. The slide emphasizes the importance of flood hazard mapping in risk assessment, urban planning, and disaster preparedness. It also aids in designing resilient infrastructure and managing water resources effectively. There is need of flood hazard mapping, risk assessment, urban planning, disaster preparedness, infrastructure design, water resource management, economic resilience, environmental protection, climate change adaptation, community awareness, emergency response planning. Flood routing plays a critical role in understanding and mitigating flood hazard. It is a process of predicting how floodwaters move through rivers, channels, and floodplains, helping to identify high-risk zones and anticipate flood behavior. This slide explains how routing enhances the design of flood control infrastructure, improves flood warning system, and informs comprehensive risk assessment. Accurate flood routing ensures that planners and engineers can develop structure such as dams and levees to minimize flooding impact on communities and ecosystems. Flood routing involves predicting the behavior of floodwaters as they travel through a river channel or across a floodplain. This process tracks the movement of flood wave along a watercourse, calculating key parameters like flow depth, velocities, volume, and discharge at various locations. Flood routing is essential for the design of flood control structure such as reservoirs and levees and for assessing the potential impact of flood of infrastructure and communities. By understanding the dynamic of floodwater movement, decision makers can implement targeted intervention to mitigate. Method of flood routing. There are two primary methods of flood routing, manual method and software based method. In manual method there are two parts, hydrologic routing, example Muskingum method, and hydraulic routing, St. Venant equation. In software based method there are five types like Flow 2D Pro, hydraulic engineering center and river analysis system, storm water management model, OpenFOAM, ANNGA based flood routing. Flow 2D Pro is a sophisticated two-dimensional flood routing models designed to simulate hydrological and hydraulic processes over grid system. It is a versatile tool capable of tackling diverse flooding problems, include riverine, urban, and coastal flood. This slide introduces Flow 2D Pro key features such as its ability to combine rainfall or runoff and flood routing processes without requiring separate models. It is widely used for flood hazard mapping, risk assessment, and infrastructure design. The software grid-based approach allows for detailed simulation and making it ideal for complex flooding scenarios. Flow 2D Pro support decision making by providing accurate flood prediction, which is critical for urban planning, emergency response, and long-term climate adaptation. Key features of Flow 2D Pro: dynamic wave momentum equation, comprehensive GIS tool, urban detail features, river and floodplain interface, sediment transport, mud flow and groundwater modeling. Application of Flow 2D Pro: floodplain mapping, urban flood risk assessment, disaster management, infrastructure design, environmental studies. This slide discusses a real-world application of flood hazard mapping in Dire Dawa, Ethiopia, a city highly vulnerable to flash floods due to its location in a valley surrounded by the highlands. The Dechetu River flowing through the city exacerbated the risk, especially in areas with unplanned settlement and inadequate drainage infrastructure. The study highlights the semi-arid climate with seasonal rainfall peaking in between July and September as a significant contributing factor to flooding. In the methodology, we calculate rainfall data for downscaling to derive IDF curve. This IDF curve gives a two things in like climate modeling and hydrograph. But the hydrograph is also derived as area, length, and slope, and from the hydrological modeling. We collect data from the soil and land from the CN second method to derive also a hydrograph. In methodology, we collect the river shape file CN third method for flow 2D modeling, and we use hydrograph for also to flow 2D modeling. From flow 2D modeling, we derive velocity and depth for hazard map, and it's all used for flood management strategy. Proposed local management strategies, structure measures, drainage system upgrades, river bank protection, flood detention basin, non-structure measures, zoning regulation, community-based flood management, green infrastructure. The total budget of project cost $1.5 million. In $1.5 million, there are four things: data collection and model setup, $5 lakh, structural intervention, $7 lakh, community engagement and awareness, $2 lakh, monitoring and maintenance, $1 lakh. Result and impact of Dairadava case study. There are four different types of data stations, which is turned to a graph from discharge and time graph of flood hazard of Dairadava cities and a flood hazard map of Dekaitu River from the different angles and different points. This table shows the comparison of ground distance versus distance of flow 2D software results for calculating the difference between both strategies and risk assessment. Findings: high risk zones. The central and eastern part of Daredava were identified as most vulnerable to flooding, with flood depth exceeding 2 meters in some areas. Informal settlement along the Dekaitu River experienced the highest risk. Flood velocity and inundation. Significant inundation in low-lying areas disrupted transportation and access to essential service. Impact of climate change. Projected rainfall increase could exacerbate flooding, affecting an additional 15% of urban area by 2040. High velocity flows up to 3 meters per second were observed near riverbanks, causing severe erosion and infrastructure damage. Case study 2: Flood inundation map and hazard assessment for the Baitarani River Basin. The Baitarani River Basin, located in Odisha, India, frequently experiences floods due to heavy monsoon, insufficient drainage, and topographic constraints. This study employs hydrologic and hydraulic models to simulate flood scenarios, map inundation extent, and assessing hazard in the basin. The goal is to provide a actionable insight for disaster management and mitigation. The study aims to develop flood inundation maps for return period of 10, 25, 50, and 100 years. Assess flood hazard zones based on water depth, velocity, and affected areas. Quantify the economic, environmental, and social impact of floods. The methodology employs advanced tools including hydrological and hydraulic models to simulate flood scenarios and map inundation extent. This case study highlights the practical use of flood hazard mapping in disaster management and mitigation. In the methodology, we observed rainfall and basin parameters. Basin parameters gives three values: loss parameters, runoff transformation parameters, and base flow parameters. This runoff transformation parameters gives simulate discharge, and observed rainfall is also gives simulate discharge. We comparison, if comparison is yes, then calibration parameters and model validation. This comparison is also derived from observed discharge data. If comparison is no, then we go to again basin parameters. This table contains budget of flood hazard of Baitarni River. Data acquisition $5,000 to $15,000. Satellite imagery $3,000 to $700. Rainfall and discharge data $2,000 to $8,000. Software and tools $3,000 to $10,000. Census of Mike flood $1,000 to $5,000. GIS software $2,000 to $5,000. Hydraulic and hydraulic modeling $15,000 to $25,000. Model development and calibration $10,000 to $15,000. Flood simulation $5,000 to $10,000. Field survey $10,000 to $20,000. River cross section $5,000 to $10,000. Ground validation and model data $5,000 to $10,000. Analysis and reporting $5,000 to $10,000. Hazard map and impact analysis $2,000 to $5,000. Final report preparation $3,000 to $5,000. Total estimated budget is $40,000 to $80,000. In the funding and stakeholders, potential funding sources like government agencies, international organizations, example World Bank and UNDP, or research grants. Stakeholders, state and local governments, example Odisha State Disaster Management Authority, communities within the basin, researchers and NGOs working on disaster resilience. Tools and technologies are used. Hydrological and hydraulic model, flow 2D probe, GIS, QGIS and ArcGIS, remote sensing, Sentinel 1 by 2, Landsat, SRTM DEM or LIDAR. This graph prepared between the discharge and time of flood hazard of Baitarni River from the time period of 2008 and 2014. And there is a pixel image of flood hazard of Baitarni River from this slide shows a map of Baitarni River and a thermal map of Baitarni River with the hazard level consistency. The results of Baitarni River case studies, flood inundation maps, 10-year return period, 12% of the basin inundated, primarily agricultural land, 12-year return period, 25% inundation, including critical infrastructure like roads and small towns, hazard assessment, low risk zones, areas with 0.5 meter water depth, moderate risk zone, depth of 0.5 to 2 meter, including small settlement and farmlands, high risk zones, depth are greater than 2 meters, impacting major towns and critical infrastructure. Economic impact, estimated damage for a 50 years flood, infrastructure $15 million, agriculture $10 million, total loss $25 million. Environmental impact, riverbank erosion and sediment deposition were significant. Flooded areas in wetlands reduces their ecosystem service. Social impact, 1 lakh people affected in the 50 years flood scenarios. Evacuation center and flood shelters funds insufficient. This slide listed academic and research sources that validate the finding and methodology discussed in the seminar. Notable references include studies on GIS-based flood hazard mapping and hydrological modeling. These sources ensure the credibility and reliability of the data and tools used in case studies. So I conclude the seminar, thanking the audience for their attention.